All right, so I'll still switch the due date to tomorrow. Okay. And tomorrow we meet in the math tank. Okay. But it's not going to be just kind of the whole day is not going to be a work day. We're still going to do stuff, but we can do some of the time as work time so we can make sure everybody is able to get the homework finished up. Okay. But I'm going to go over a few of these now. That way, just in case it's something simple that we can clear up and try some more tonight if anybody's stuck on anything in particular. So this one, we're going to need a special rule. What rule are we going to need? Quotient rule. Because we've got a function of x in the numerator, a function of x in the denominator. So we've got two functions of x being combined with division. So we're going to need quotient rule. When you're doing your homework, I suggest you copy this problem over onto a piece of paper and work it out on a piece of paper, and then transfer the answer back into MyLabs Plus. And make sure you copy it right. Yes. If you get it wrong, don't just get mad and dismiss the wrong pop-up that comes up. Actually read the pop-up, because sometimes it'll say you have it right, but they want you to simplify it a certain way or write your answer a certain way. So you might see the pop-up come up saying you have it wrong and get mad and then redo the whole thing, where really if you just read it, it says you have it right. They just want you to simplify it a little bit more or something, and you save a whole lot of time because they just want you to simplify it. All right, so make sure you read that pop-up. If you got it wrong, make sure you read the pop-up that comes up. All right, so we've got 4x squared minus 7x plus 1. Is this 5? We're at number 5. Problem number 18. Over 2x plus 9. And we want the derivative for this. So we've got to use the quotient rule. All right. There's no chain rule in here yet. Chain rule is the section after this. All right. So you shouldn't have to do any inside-outside stuff. What do you need me to do? Come on in.
So,
all right, so we're just going to do this one real quick. We'll talk about more homework tomorrow because I want to make sure that we at least talk about enough implicit differentiation that we can start some homework possibly on it. So this one's just quotient rule. We haven't, at this point in our homework, we haven't talked about chain rule yet. So we've just got to remember, always start with the derivative of the top, okay? The top and the bottom are just polynomials. So we're just doing power rule on all the pieces to get our derivatives. So for the derivative of the top, we just have to do the power rule on each of the pieces. So for what is the derivative of the top? 8x minus 7. Yep, the derivative for the first piece, if we bring down the exponents, there's already a coefficient there, so it just gets multiplied by the coefficient that's already there. So we have 8 times 2. New power is 1 smaller, so it's going to go from 2 to 1, so 8x. And then the second piece is linear. You can do the power rule on it, and the 1 comes out front, new power is 0, but also you can remember that anytime you have a linear expression, the derivative is just the coefficient. And then the last term is a constant, and the derivative of a constant is 0. If you want to, you can put an x to the 0 next to it, and it does follow the power rule as well. And then you match that up with the original bottom. Oops. And then quotient rule has a plus or a minus. Minus. And then we flip-flop it. Original top. Derivative of the bottom, which is just 2. All over bottom squared. And most likely, MyLabs Plus is going to want you to simplify the numerator. Okay, so we're going to want to FOIL out this stuff. And then distribute the 2 and distribute the minus. Be really careful with the second term in the quotient rule because that minus applies to everything behind it. So it's going to have to get distributed. So we're going to want to FOIL out that 8x minus 7 times 2x plus 9. We get 16x squared. What am I writing? Plus 72x minus 14x minus 63. And for now, I'm just going to distribute the 2. And then in the next step, I'll distribute the minus. If you find yourself making a lot of careless mistakes, then you might want to slow down the number of steps you're trying to do at a time. Okay? So I'm not going to distribute the 2 and the negative at the same time. I'm just going to distribute the 2 for now. So that's 8x squared minus 14x plus 2. And now I can get rid of those parentheses if I distribute the minus. This 2x plus 9 and this 2x plus 9 cannot cancel because of the minus in the quotient rule. You can only cancel between the numerator and the denominator if they are both completely factored. And if there is subtraction, then it's not factored. Factored means all of those pieces are being multiplied, and they're not. That minus there in the middle means it's not all multiplication. There's subtraction in there. So you cannot cancel them. So we've got 16x squared plus 72x minus 14x minus 63 minus 8x squared plus 14x minus 2. And we'll combine all the like terms in the top. You don't need to FOIL out the bottom. You'll always have that original denominator squared in the bottom. I would just leave that one alone. But how many total x squareds do we have? We've got 8 of them, because there's 16 here, and then minus 8 of them there. So we've got a total of 8x squareds. And we've got 72x minus 14x plus 14x. So that's just plus 72x. And then we've got minus 63 minus 2. It's going to be minus 65. I would not FOIL out the bottom. The only reason we mess around with the top is because parts of the top are factored, and then there's subtraction in between. So we've got this mix of all different operations. So it usually wants it either all factored or all multiplied out. It doesn't usually want the mix of factors and subtraction. So it either wants one or the other. So it just multiplies it all out. So unless you have some crazy powers like fifth powers or ninth powers or square roots, we had just some simple stuff like some foiling and distributing a 2, so we just go ahead and do it. So tomorrow we can talk about number 9 is also a quotient rule, but it requires us to do the derivatives of some e's. So what's the derivative for e to the x? Is e to the x. So it's just quotient rule again. We just need to remember that the derivative for e to the x is e to the x. Number 20. Number 20, I would consider that to have a chain rule in it. Because it's got e to the negative x in it. That's technically a composite function. I'm surprised about that one.
So that's e to the x to the negative 1.
It's right, it's e to the negative 1x. So anytime you've got an exponential function and the exponent is anything other than an x, then you would consider it to be a function plugged into the e, and you would think of it. Yes.
All these functions and stuff like that, I mean, I know they don't all look the same, but they kind of do. Are we going to know when it's like a composite or not? I don't know.
So with the composites,
Like, is there a way that we can look at them and remember, like, this is composite, this is
Composite as a chain rule?
so the way that I recognize something as a composite is I don't see the separate x's. So it's just another operation applied to something else that already has x's. So let me write that and show you. So product versus composite. So if we had a square, that's not a good example, a sine times a square root. If it's a product, you'll see x's in both of them. So you would see a sine function with its own x times a square root with its own x. If it's a product, they will have their own x's. Okay, so it's two separate functions of x being multiplied together. If it's a composite, they won't each have their own x. Only the inside function has an x. And then the outside function is just, all you see is the operation applied to the inside function. So we'll see the x on the sign, and then we'll just see the square root symbol. The square root symbol won't have its own x. So for a composite, we would see the square root symbol, but sine x is inside of it. Okay? So the square root doesn't have its own x. The sine is inside of the square root. So that's how I know it's composite. So if square root has its own x and sine has its own x, and they're being multiplied, then I know it's a product. Or if they're being divided, then I know it's a quotient. But if one function is inside of another function, then it's a composite. So that sine function is like physically inside of a square root. That's a composite. So square root all by itself could be a function, but only if it has its own x and it's written by itself with its own x. But if you see a square root symbol and there's something else inside of it, then it's a composite. Mm-hmm. Yeah, so this one would need product rule. This one would need chain rule. the answers would have similar pieces because in both processes you would do the derivative for sine, you would have your power rule for your square roots, but the final answers are not going to be the same. But you'd end up doing a lot of the same derivatives. All right, so 3.8 is interesting and different. So first we're going to talk about what the word implicit means. .8 is implicit differentiation. Everything we've been doing to this point has been explicit. It's been explicit. So you may be familiar with the term explicit, just like in everyday life in English, not really necessarily in math terms. Usually when something is explicit, like it's obvious. So in math, when an equation is explicit, it's solved for y. It's y equals a function of x. An explicit function is solved for its output variable. And almost everything for us right now has been y is the output, x is the input. So y equals 1/2 x plus 3. That's an explicit equation. X is the input, y is the output, and this equation is solved for y. Y is all by itself on one side of the equation. Y equals x squared plus 5 over 2x minus 1 is an explicit equation. Y equals the square root of 2x minus 3 is an explicit equation. So the one thing you need to remember in order to understand implicit differentiation is that y is always a function of x. Whether we know what it is or not, whether we know what it's equal to or not, y is always a function of x. Okay? So a function is in implicit form if the x's and the y's are all jumbled together. Like an equation for a circle is typically given an implicit form. A lot of equations that don't represent functions, like circles. A circle is not a function because it doesn't pass the vertical line test. Those have to be written in implicit form. So a function or equation is written in implicit form. if it is not solved for the output variable. If it says anything other than y equals, and it doesn't always have to be x and y. We can use other variables like we saw at the end of class yesterday. So some examples of functions in implicit form. Like Brandon said, equations of circles are almost always given in implicit form because they're not functions. So x squared plus y squared equals 4 is the equation for a circle centered at the origin with radius 2.
Is it possible to correct that?
Yeah.
Like number 84?
Yeah. You would go to the draw function. We don't typically type it into y equals. We go to draw and there's an option for circle.
Yeah.
And you type in the center and the radius. You do 0, 0, 2. If you want to draw it in y equals, you've got to solve it for y, and you end up with a plus or minus square root, and you do like the positive in y1 and the negative in y2, and it's going to draw it as a top half and then a bottom half. The y equals in your calculator only draws functions. And this is not a function, so you would have to type it, the top half and the bottom half in separate. A couple more examples of implicit equations. Xy minus 2x equals 3. It is not solved for y. Yes? Point slope form. Yeah, technically point slope form is implicit because it's not solved for y.
So the variables don't have to be on the same side.
Nope. Nope. It's not solved for y. So for us to say y minus 4 equals 2 times x minus or plus 1, technically in that format, it's not solved for y. It would be very simple for us to get it solved for y, but it's not solved for y. So we could say it's implicit. Implicit differentiation is not simple. So once you see the process we're going to have to go through, usually one of your first options is if we can get it solved for y and avoid implicit differentiation, we want to do that. So something like point slope form, we would definitely want to add that 4 over and avoid implicit differentiation. Y squared plus 2yx minus 1 equals 0.
That, to make it implicit, could you just solve for x? Is it possible to just make it, explicit if you just solve for x instead of y?
No, because x is the input variable. Nope. It specifically has to be solved for the output variable. So that's a good point, though. This one would be pretty easy to solve for the output variable because there's only one y in the problem. This one would not. You would not want to waste a bunch of time trying to solve that for y. I don't even know if it would be possible to solve that one for y. And try to get it written explicitly so you can do normal derivative rules on it. Because it's a quadratic in terms of y. Y appears multiple times in different forms. But you can't divide by variables because x might equal 0. So we want to avoid dividing by variables. So we could write the yellow one explicitly since y only appears once. It would be pretty easy to solve that one for x. That second one where we've got y squared and y, where y is quadratic, we do not want to waste our time and our brain cells. And algebra already is not most of our strong suits. We don't want to waste the time trying to figure out what y is equal to. It would be easier for us to just learn implicit differentiation since our goal is just to get the derivative. So implicit differentiation would just be a quick way for us to get the derivative without having to spend a whole bunch of time trying to figure out what y is equal to. The key here with implicit differentiation is you have to remember that y is a function of x. Y is a function of x, but when it's written implicitly, we don't know what y is equal to in terms of x. The y is all jumbled in with the x's, okay? So when we try to do the derivative and we see a y in the problem, we have to remember that it's technically a bunch of x's. And we have to treat it like a bunch of x's, and we need to do its derivative like it's a bunch of x's. So that's the trick for implicit differentiation. So there's a couple different notations that people use. When you get to the point where you have to do the derivative of a y, some people like to use y prime, and some people like to use dy dx. I personally like to use dy dx because y prime looks way too similar to the y, and sometimes they get confused. So to denote the derivative of y, you can use y prime or dy dx. And you're going to see me using dy dx just because I want it to be very obvious that it's different than y, and I think y prime looks way too similar. But if you've done this before, I know about half of you have had calculus before. If you've already done this before and you're used to using y prime, then that's fine. I want us to look at an explicit example first, just for notation purposes, and see how it's going to be similar when it changes to implicit. We want to find the derivative, which is dy dx. And we're given y equals 5x squared plus 9x. The y is all by itself. So to go through and take the derivative of everything and come up with dy dx is going to be easy. So if I just enclose this whole thing and say, all right, start applying your derivative rules. That's going to give me dy dx equals the derivative of y with respect to x equals, and then we apply our derivative rules on the x's. So when you take the derivative of y, you either write y prime or dy dx. So right here, when I took the derivative of the y, I wrote dy dx. And then when you take the derivative of the x's, you apply your derivative rules that we've been learning. So what's the derivative for 5x squared? 10x. And what's the derivative for 9x? 9. So dy dx equals 10x plus 9. If this same exact equation was written implicitly, we could still get the same answer. Y over x minus 5x minus 9 equals 0. We want to find dy dx. What we're going to do is we're going to go through and we're going to take the derivative with respect to x of everything. And you have to remember, this one is written implicitly. And even though it says take the derivative with respect to x, and that y is not an x, it doesn't say x, we have to remember when we do implicit differentiation that y is always a function of x. Y is always a function of x. So even though we don't see x's there, there are x's there. We just don't know what they are. So technically, we have to do quotient rule here. Y is a function of x. So we have a function of x on top, we have an x on the bottom. We have to do quotient rule for that first piece. So if I'm going to go through and I'm going to apply all my derivative rules on everything in this equation, we start with the derivative of the top. How did we say we're going to write the derivative of y? dy dx. and you multiply that by the original of the bottom. And then subtract original top, and then the derivative of the bottom, all over bottom squared. And then what's the derivative of minus 5x? Minus 5. What's the derivative of minus 9? 0. And what's the derivative of the equal 0? 0. So we still have equal 0. We were asked to find dy dx. So we're not done until we have an answer that says dy dx equals something. So the rest of this is algebra. The rest of the problem is going to be algebra to get dy dx all by itself. So we're going to start moving terms over to the right so that we can get dy dx all by itself. So we'll add the 5 over. What should we do next? Multiply the x squared over. We're trying to solve for dy dx. We'll add the y over. And then we'll divide that x over. And since there's 2 terms on the right, I'm going to go ahead and divide them individually. We've got to divide everything by x. And I get dy dx equals 5x plus y over x. Does that look the same as what we got a minute ago? 5x plus y over x when we did this explicitly? 5x plus y over x. If you did it explicitly a minute ago, compare it. What's different now? There's our explicit answer. We have a y in our answer now. And that's because if the problem started implicitly with the x's and y's jumbled together, most likely the derivative is gonna end implicitly with x's and y's jumbled together. But if you don't want your derivative to be implicit, you can always go back to the original expression and do some replacing. We can figure out a replacement for the y over x. I can replace the y over x because look, in my original equation, I have y over x. What is y over x equal to? I can solve that for y over x. Y over x is equal to 5x plus 9. So if I want my dy dx to be only in terms of x, I can go into that implicit derivative and replace y over x with 5x plus 9. And now my derivatives say the exact same thing. So the problem was that when I start with an implicit, I might get an implicit answer. If we need them to say the same thing, or if we want to be able to compare, we just have to go back to that original equation that were telling us the relationship between x and y and replace those y's. So it is the same thing. We do get 10x plus 9 again. So I'm going to give you some some concrete specific steps for solving implicit problems, and we're going to look at a couple more. We're not going to compare explicit, implicit. I just wanted to show you that we get the same thing. The most important thing to remember is that when you see a y, it is a function of x. You have to treat it like an x. Its derivative is dy dx. If it's ever multiplied or divided by an x, you have to do product rule or quotient rule. If it is inside a square root or it has a power, you have to do chain rule on it because it is a function of x. Okay? Y is a function of x. And then our goal usually is to solve, after we've applied the derivative rules, our goal usually is to solve for dy dx. Because dy dx is the derivative, and dy dx is what represents our slope, which is what one of the main applications for these derivative problems. I'm not a big fan of steps, but I know some other people are. And this is probably a good, this section can be complicated, so sometimes it's good to keep your thoughts in order. So if you're ever given an implicit equation and you're asked to find dy dx, so that's how we recognize that we need to do this. So we have to remember what implicit means. It means it's not solved for a while. The x's and y's are kind of jumbled together. We're going to go through and we're going to take the derivative of everything in the equation with respect to x. Make sure that you're using your product rules and your quotient rules and your chain rules. If you have any x's multiplied together, if you have any x's and y's multiplied together, that's product rule because y is a function of x. So make sure you're using your special rules as well. So we just go through and we differentiate everything. And that's most of the work right there. So remember, if you get to the point where you have to do the derivative of a y, we do dy dx. If there's an operation on it, we'll have to do chain rule, because it would be like a function of x with another operation applied to it outside, and we'll look at an example of that. So remember that the derivative of y is dy dx. There may be multiple y's in your equation. So when you apply your derivative rules, you might have dy dx appear multiple times. If we're asked to find dy dx, our goal at the end is to have dy dx equals something. So once we apply all our derivative rules, after that, we're just doing a bunch of algebra to find, to get dy dx all by itself. So once you apply all your derivative rules, we want to collect all of the terms that have dy dx on one side of the equation and all the terms that don't have dy dx on the other side of the equation. And I usually say collect all the ones with dy dx on the left and all the ones without on the right. So this is how we can take a problem that has dy dx appear multiple times and then just kind of simplify it down to just appearing once. Because if we collect all those terms that have dy dx on the left, we can just factor the dy dx out, and then it will just appear once. So we're going to factor dy dx out of all of those terms on the left. And then we'll just have to divide over whatever was left from the factoring to solve for dy dx. So step number 2, 3, and 4 is just algebra. Really, step 1 is just the calculus stuff. These ones do not say solve for dy dx. They're not equations, okay? They just want us to go through and differentiate everything. So this is just practice with step number 1, where we just go through and differentiate everything with respect to x. Just practice with step number 1. So we go through and apply all your derivative rules on the x's. Y is a function of x. So you are still applying them to the y's as well. But the y's have an extra step because we also have to say dy dx. So since we're differentiating with respect to x, that means you treat the x as completely normal. So what's the derivative of x squared with respect to x? It's 2x. You treat the x as completely normal. For y squared, we have a little bit of extra work to do. Y squared, y is a function of x. So that's like saying we have some function of x and it's being squared. That's a composite function. Y squared is a composite function. So we've got to do the derivative of the outside times the derivative of the inside. So you're going to start with the power rule, just like we did on the x squared. So if we do the power rule on y squared, what do we get? 2y. And then we also have to multiply by the derivative of the inside. So the inside is just the y. And what do we say the derivative of y is? Dy dx. Anytime you do a derivative of y, you're always going to have a dy dx after it. You're going to do your normal derivative rules and then also dy dx. Normal derivative rules and then also dy dx. So it says take the derivative with respect to x. That means normal derivative rules on x's. We're also going to do derivative rules on y's and then attach a dy dx. And technically the reason we do that is because of chain rule. Okay? Because y is a function of x. We just don't know what it looks like right now. But we would have to do power rule and then also multiply by the derivative of the inside. We just don't know what it is. But if at some point we find out what it is, this tells us what we're supposed to do. So it's 2x plus 2y dy dx. Ooh, I don't want equals on there. I'm sorry. No equals yet. We've got x squared y plus y cubed. We just want to go through and take the derivative with respect to x of everything. It's implicit, okay? It is not solved for y, but you have to remember y is a function of x. So as long as we remember that, what is special about that first term? X squared times y. When we do the derivative of it, x squared times y, and we want to do the derivative. Y is a function of x. So I've got x squared times a function of x, and we want to do the derivative. It's not a composite because we said times. So it's product rule. We have to do product rule on x squared times y. We have to do product rule on x squared times y. Even though it's two different letters, you have to remember that y is a function of x. Okay? Y is a function of x. Anytime you see multiplication between variables, you're going to do product rule. So we're going to do the derivative of the first piece, which is what? We're almost done, guys. 2x. And we're going to match it up with the original of the second. So just times y. And then flip-flop. Original of the first, x squared. Derivative of the second, dy dx. That is just the derivative of the first term. Okay, I've got the derivative for x squared is 2x, matched up with the original of the second, plus original of the first, derivative of the second. That is product rule for my first term. And then we also need the derivative for y cubed, which is a chain rule. Because remember, y is a function of x. So that's like saying a composite f of x with a cubed outside. So first we'll start with derivative of anything cubed is we do power rule, 3y squared. And then the derivative of the inside is dy dx. So we've got 2xy plus x squared dy dx plus 3y squared dy dx. So if you look at how we did y cubed, we did normal power rule, and then we also threw a dy dx on it. So you always do normal derivative rules on your y's, and then always attach a dy dx to it. If you've got a product between x's and y's, you have to do product rule. If you've got a quotient between x's and y's, you have to do quotient rule. All right, so let's do one equation start to finish. And we'll talk about this a little bit more tomorrow, as well as go over homework. So our equation, we want to calculate dy dx if we have y squared minus 5xy equals 3x squared plus 2. Our end goal is to say dy dx equals something. Dy dx equals something. And dy dx means derivative. So the first thing we want to do is go through and take the derivative of everything. It's the derivative with respect to x, which means treat x as completely normal. If you've got to do the derivative of any other letter, you'll still apply normal derivative rules, but then attach the extra piece to it. So in this case with the y's, we'll do normal derivative rules on the y's, but then also attach dy dx. And then if we ever see product quotient of y's and x's, we'll do product or quotient rule. So what is the derivative for y squared? 2y would be the normal power rule, but because it's a y, we also say dy dx. Okay? So 2y dy dx. And then I've got a minus sign, so that transfers down.
Oh, wow.
It's not 5y.
It's not 5.
We've got to do product rule there because I've got an x times a y.
Isn't it 5x something?
It's not 5x.
5.
This is,
y minus x dy dx.
I am going, this is what I'm going to do. This is how I like to do it, but you don't have to.
It's basically you distribute it.
So wouldn't
It's
it be,
same anyway.
Mm-hmm.
wouldn't that be 5y times 5x divided by x?
Yes.
Yes. That's not what you said a second ago, though.
I
Minus.
said the first part of it.
Okay, you said the first part.
Don't forget to put the minus in there.
Yes.
So minus 5y.
All right. So the second term is 5 times x times y. So we've got variables multiplied together, which means we have to do a product rule. So the minus just gets transferred down. You can just transfer the 5 down if you want, but then on the next step, you're going to have to distribute it to everything, and that's perfectly fine. What I like to do is I like to group my 5 in with my first variable. That way I don't have to do on the next step, distribute the 5. Either way, you'll get the same answer. It does not matter. But I'm just going to group my 5 in with my x, and then that takes care of the distributing. So my first function is 5x. My second function is y. They are being multiplied, so to find the derivative, I need to do product rule. What is the derivative of 5x? 5, and we're going to match it up with the original of the second. So y. And then product rule has a plus. And then we're going to do the original of the first times the derivative of the second. So the derivative of y, dy dx. And then I have an equal sign. That transfers down just like the pluses and the minuses and the coefficients. We want the derivative for 3x squared. 6x, it's an x, so just do it normal. And then the derivative for 2 is 0. So dy dx appears in here twice. So we're going to want to consolidate the terms that have dy dx to the left and the ones that don't to the right. Before I do that, though, I'm going to have to distribute this minus sign. So we've got 2y dy dx. Everything after this point now is just algebra. So I just distributed my minus.
2y dy dx minus 5x dy dx.
I'm going to keep these two guys here on the left. But I'm going to add that 5y over to the right. Step number 2 was to collect all dy dx terms on the left and anything that doesn't have dy dx on the right. Because if dy dx appears multiple times, we want them all together so that we can factor it out of them and then only see it once. So now everything on the left has a dy dx, so we can factor it out. So what do we have left over when we pull out the dy dx from the two terms on the left? If we pull out dy dx, we'll have 2y left in that first term, and we'll have minus 5x left in the second term. And then the last thing we need to do, because remember our goal here is to solve for dy dx. We want this guy all by himself, and they are combined with multiplication now that we've factored. We just need to divide the 2y minus 5x over to the right. So we'll get dy dx equals 6x plus 5y divided by 2y minus 5x. And we don't need to worry about replacing the y like we did earlier. We only did that earlier just so we could compare our explicit and our implicit answers and show that they came out the same. So this is a perfectly acceptable final answer. So we've solved for dy dx implicitly. So the key here, and we'll do some more examples next class, the key is to remember that y is a function of x. And anytime you're asked to differentiate with respect to x or find the derivative with respect to x, you apply all normal derivative rules on the x's. You're also going to apply your derivative rules on the y's, but you have to treat y like a chain rule. So if y has any other operations applied to it as well, you have to do normal derivative rules as well as the derivative of y, which is dy dx. So we're going to apply normal derivative rules, which is our power rule, our product rule, our quotient rule. But if you look back, every single time we did a derivative of y, we also have a dy dx after it. And that comes in because of chain rule. We did normal derivative rules, which is the derivative of the outside, and then times the derivative of the inside, which is the derivative of the y, which is dy dx. Because technically y is a function of x, but y is not given explicitly. So we don't technically know what y is equal to with respect to x. But if we did, our next step would be to take the derivative of the inside. So that there is, the dy dx is kind of like a placeholder saying, well, the next step is to take the derivative of the inside. We just don't know what y's representation is in terms of x, but we still need to do it. Those are the rules for derivatives.